Hi, I'm Doug,
I'm Vera.
and this is our rocket.
Our goal in building this rocket was to have it reach as high an altitude as possible with the given materials and motor. Additionally, we were challenged to keep an egg in the nose cone and return it intact to the ground with the use of a parachute to slow descent. We designed the fins so that they held a middle ground between being lightweight, aerodynamic, and large in surface area. We wanted them to be lightweight and aerodynamic to reduce the retarding effects of gravity and drag respectively, in order to make the rocket achieve the highest possible altitude. On the other hand, we wanted them to have a decently big surface area, in order to provide more stability when the rocket encountered unbalanced forces, such as wind gusts. We opted to use the high-definition camera for filming the onboard footage during flight. We felt the higher quality video made up for the added mass. As such, due to the camera's shape, we mounted the camera fully inside the body tube of the rocket, with the camera's lens facing outward, through a hole cut in the side of the tube. We made this hole just large enough to allow for slight movements of the camera during flight, to enable the camera to film the entirety of the flight. The length of the rocket, from nose to tail, was 21 3/4 inches. The diameter of the body tube was 1 5/8 inches. What is now being shown is the thrust stand data for a D motor, the closest in size to the one used in our rocket from the available data. From the graph, we can determine that the maximum thrust provided was roughly 24 newtons at the 7.5 second mark. The thrust then quickly regressed to just under 10 newtons for the duration of the burn. After the burn, the engine cut to 0 newtons for about 6 seconds before providing a 4 newton ejection charge in the opposite direction of the main burn.
What is now shown is the actual plot of our rocket's trajectory as provided by the altimeter in the payload. This plot fits very well with our initial expectations. Before apogee, the rocket gained altitude very quickly due to thrust provided by the motor. Once apogee has been reached, the rocket slowly descended to the ground with the help of a parachute. Despite the parachute becoming tangled during ejection, it must have at least partially unfurled, as otherwise the rocket must have fallen much quicker than what's shown in the plot. During the process of designing and building this rocket, we learned multiple important things. Among them, how a model rocket motor works, and in turn, how to design a rocket based around a motor, like having a segmented body to allow the ejection charge to launch the parachute, and the like. Also, how various aerodynamic forces act on a rocket in order to either promote or prevent its vertical motion, like thrust, gravity, and unbalanced forces. And in a more practical sense, that it is very important to pack a parachute properly, lest it fail to open, allow your rocket to make too heavy an impact, as our cracked nose cone and broken fin can attest.
3B going in 5, 4, 3, 2, 1, 0.